This is the final podcast in our series on the gas laws, and this one is looking at real gases. Real gases are not ideal gases. You see, the particles aren't ideal. They do take up space, and they do interact with each other, especially polar molecules. So to account for these facts, correction factors are introduced into the ideal gas laws. And there are correction factors for both the volume and for the pressure. The volume correction is because the actual volume of free space in the sample is less because gas particles take up some of that space. And indeed, the more molecules there are in the sample, the greater the concentration, the effect will be greater. Likewise, the bigger the molecule, the more the effect of it taking up some space. And so to account for it, we have a subtraction of an NB unit, that is number of moles times a correction factor, B. And the B constant is different for each gas, and you'll find them in tables. We also correct for pressure. Because real molecules are attracted to each other, the pressure on the container will be less than the ideal gas law would calculate. The magnitude of the effect depends upon the type of molecule. Polar molecules are more attracted to each other, so they'll show a greater effect. And indeed, if you have more molecules in the sample, then they're going to be hitting each other, and they also will not impact the walls of the container as often. And since when we're hitting other molecules there are two of them, the correction factor is actually squared, and so the pressure observed is in fact pressure minus a squared term and a unit of A. And once again, A is something you will find in a table. When we substitute those two correction terms into the ideal gas law, instead of getting PV equals nRT, we get what's in front of us, which is the corrected pressure times the corrected volume equals nRT. It's an equation more you need to understand than you're actually ever going to use. Well, where do A and B come from? Experimental data have been collected, which is why they're different for every single gas, and you'll look them up in a table. But in general, large molecules have a larger B value. That makes sense since B is the volume factor, and polar molecules will have a larger A factor since attractive forces depend both on size and polarity. What I'd like you to do is take a look at these graphs, which plot PV over nRT versus P. Now, for the ideal gas law, and for an ideal gas, you'd get a straight line because PV equals nRT. But not so with real gases. And what I'd like you to do now is stop the podcast and examine both the graph on the left, which has four different gases in it, and the graph on the right, which is for nitrogen at different temperatures. And draw some conclusions. See if you can make some sense out of this. If you've started the podcast, what you've discovered is that at low pressures, PV over nRT was below 1, meaning the PV term was smaller than the ideal. And the way we would explain that is that the attractive forces between the molecules reduce the pressure and the observed volume. Hopefully at high pressures you saw that PV over nRT was above 1, and it increased steadily, meaning the PV term was larger than ideal. Well, that would be due to the volume of the molecules becoming more and more significant as the pressure rose, since the higher the pressure, the closer the molecules are together. You also notice in the one on the right, for temperature, that as the temperature rose, the effect became less and less.